What's up everybody, this is Cakez and welcome back to another tutorial in which we add font rendering to the game. Since I don't want this to be a tutorial on how to open and load in TrueType font files, which is what we're going to be using, I want you to download FreeType. But unfortunately, it has been such a long time for me since I last downloaded FreeType. I don't actually know exactly the version that I'm using. If you want to get the FreeType library, you go to the repository and I will link this in the description, third party, and then please make sure that you download the FreeType folder, the .lib folder or the lib folder, and the ft2build.h file. Make sure that you download these, or if you don't want to follow along completely, clone the entire repository. Should be fine too. It is up to date with this tutorial. But once you have downloaded the files, I want you to put them into the third party and then paste them right here. The FreeType build, the lib, and the FreeType folder. The lib will contain the library and the FreeType folder will contain a bunch of header files that we need. The one that we are going to include is the ft2build.h. And this is where we are going to begin in the GL renderer. First, I would like to do some cleanup. This is a game include or an in-engine include, so I want to put this at the top. Right below the PNG files include, I want you to include the ft2build.h. This is how we're going to include it. And then we scroll down right below the callback, but above the GL init function. This is where I want you to create a new function, which is called load font. This load font function takes in a path to a TrueType font file and a font size. You can think of it as the size in pixels for each character. So for example, if you supply 16, then each character will have about 16 pixels worth of space that it will use in a font atlas, which is just a PNG file or a texture that we will then upload to the GPU. Initializing FreeType is very simple. We just call init FreeType using a font library structure on the stack. Then we generate a font face. We also have to do initialization here, and then we set the size using the font size. This is where we actually scale it. And then further down below, this is basically creating a buffer on the stack, then looping over all of the glyphs and then copying the data from the glyphs into the atlas and then uploading this atlas to the GPU. So if we start with the padding, this is basically how many pixels of padding does each character have next on top of each other. Otherwise, it could be that if when we draw one glyph, that this character will have some pixels from the other character inside of it. And so we're just going to avoid it by using a padding. Then we are keeping track of the row that we are inside of our texture atlas and then the column. Currently, we are going to create a 512 by 512 texture, and then we are creating a stack array of characters right here. Now we have to be careful with this. If this gets too large, this can obviously exhaust the stack, but for now this is fine because we are not allocating a lot of stuff on the stack anyways, just to keep in mind. After that, we go through the glyphs 32 to 127. So in case you're wondering what that means, 32 is the space character, and then after that we have the decimal numbers for the exclamation mark and so on and so forth. All of the characters up until 127, which is the delete character. For each glyph index we get a character index, which is some sort of glyph index, a special glyph index from TrueType, and then we load the glyph and then we render the glyph. Then below that we are doing some math to check whether the glyph will actually fit into the current row. If not, we're going to increase the rows and then reset the column back to 0 or the padding. Below that we generate our font height, and we don't have that right now, so we could go into the render data right here and then generate an int font height. This will make this go away. And then we also need to get a maximum function that takes in integer values, which we don't have. So we need to switch for that into the schnitzel lib, into the math stuff section. And I would like to post into functions here. We have a minimum function for ints and a maximum function for ints. Now that we have this, we need to switch back to the renderer, and then it should be okay right here. So basically what we're doing is we are taking the ascender and then we are removing the descender of the glyph, and we are bit shifting this down by 6. I don't know 100% why you have to do this in FreeType, but in order to get correct values that correspond to actual pixel values, you have to bit shift down by 6. And this is actually also something that is in the documentation. You can see this down below here as well. Essentially what we are trying to do here is we are going through all of the glyphs, and then we are generating the font height of the highest glyph. The glyph with the highest ascender minus descender, that is the font height that we want to pick. You can also take a look at learnopengl.com for text rendering. This is where you have some data about what we are going to be using. Bearing X, origin, advance is very important for us. Then we have a width, and a height. All of these things are very important to us and we're going to be using them. I will put the link to this in the description as well as the link to the ASCII table if you want it. Okay, now that we have the font height, we need to loop over the bitmap from the glyph, and then we're going to do some math using our texture buffer to copy it into the correct location. Now, I don't want to go into too much detail, but basically what we are doing is we're going through the rows and columns of the bitmap, aka the X and Y coordinates, and then we are copying the glyph one by one into our texture atlas. Once we are done with this, we also have to store the data on the glyph. So basically the advance and the offset is very important to us. And of course the size, which corresponds to the sprite size in our usual sprite system as well, right? We need to know, well, how many pixels of this texture do we actually draw for this glyph? And so in order to do that, we need to generate a structure called glyph, and we do that in the rendering interface. Right below the draw data, I want you to create a glyph structure. This has a vector to offset. This is the amount of offset for the glyph. Then the advance. This corresponds to how many pixels do we skip until we draw the next character. And then the texture offset and size corresponding to our texture atlas that we are generating right here. And then below the font height in the render data, I want you to generate an array of glyphs with 127 characters. Okay, after that, switch back to the GL renderer, and then we should be able to get a handle to the glyph, and then we fill in the data. The width and rows of the glyph is going to be the size. This corresponds to our quad size in the texture atlas. The advance is basically the same thing that we do with the font height up here. We have to get the advance and then bit shift it down by 6. Again, this is in the documentation of FreeType. And then the offset is the bitmap left and bitmap top of our glyph. This is basically for each character, we need to offset this to a certain position so that they all align properly within some sort of line. And this line is the following line right here. It is called the origin line. Okay, and then after we are done, we are filling in the data for the glyph. We increase the column count by the bitmap width plus the padding. Basically, this is in our texture atlas again. We have generated a sprite in there, and then we need to offset that again so we can fill in the next slot. So we do this for all of the characters, and then once we are done with this, we make sure that we clean up everything. So we are done with the font phase and we free the library, and then we need to upload our texture to OpenGL. And this is where I also have to go into what the bindings are, and because I made a mistake the last texture tutorial and I want to fix that now. But first we need a font atlas ID in our GL context. So go at the very top below the projection ID. This is where we generate our font atlas ID. And then if we switch back down again, everything should be fine here. So what we are doing is we need to generate a texture slot that is different from our last texture slot, which is the texture atlas. We need a font atlas and a texture atlas. And so if we switch over to the fragment shader, you will notice that in the bindings, I accidentally set a location 0. This is actually a mistake. This is supposed to be a binding. And what this binding means is if we set this in the shader, then it maps to texture locations, texture slots. What OpenGL keeps track of is texture slots. And these correspond to texture 1, texture 0, the same thing that I was talking about earlier. And if you want to make sure that texture slot 0 is always going to be this uniform, then you can set this in the shader using binding 0, or you can omit the binding, and then in the GL renderer, what you have to do is when you generate your texture, you have to query the GL uniform location by calling GL get uniform location, taking in the program and then the name of the uniform. And this would correspond, of course, to the texture atlas. And then if we wanted to map this location to a texture slot, you would call GL uniform 1i, and that basically binds a location to a texture slot. And if you do not want to do this, we are going to hard code this, meaning this texture 1 will correspond to binding 1. And we make sure that this is the case by setting the binding in the fragment shader. So we copy this and then call this font atlas and assign the binding 1. Now the font atlas will be in texture slot 1 and we can use it in the engine. Yeah, when we fill in the data for the image, we use a texture 2D. We say that it's a red component only, so basically one component. We set the data to an unsigned byte and we supply our texture buffer, which is the allocated texture buffer on the stack. Now that we have uploaded the texture, we also need to call this in the GL init function. So I guess below where we generate the texture, right before the transform storage buffer, I would like to create a section. We're going to load a font called Atari Classic. And if you want to use another font, you can do that. It's very simple. You just have to go to Google and then do TTF fonts. pixel art maybe. And then, for example, you could use one-on-one fonts or something else if you want to. Then go through these here. Maybe you find something that's more interesting. If you want to use my font, you go to the GitHub and then download the TTF file there. In order to do that, we have to first create a new folder under assets, call that fonts. And then inside of fonts, I want you to reveal that in the Explorer, and then we can copy the file over here. Once you have the TrueType font file, you should be able to close this, and then this function will load in the font. Now that we have a way of loading font, we also want to draw text. So we switch over to the rendering interface, and then at the very bottom below the draw sprite function here, we're going to add in another section for interface UI font rendering. The draw UI text function takes in a text, a position and some sort of text data. We'll get into this in a second. We assert if we have a text supplied or not. If not, we return. Otherwise, we keep track of the origin and then we loop over every single character in the text. If we find a new line character, then we set the position on the Y coordinate and increase that by the font height times the font size, and then we reset the X position to the origin. Additionally, you could also continue here so you don't draw this backslash character, and then further down below, when we actually have a character that we want to draw, we get the corresponding glyph, and then we generate a transform on the stack. We make sure that the material index of the transform, which is something we're going to add in a second, is the correct material index based on the texture data, and this is a good time to talk about texture data. Texture data is something that we want to supply to UI text functions, and it is going to be different than draw data. For example, we don't need an animation index. Text data as well as draw data both have a material. On top of that, text data will have a font size and rendering options. In order to complete this, we have to switch into the shader header and then implement this material, because we are going to copy this to the GPU. A material will for now just hold in color. So switch over to the shader header, and then below the transform, I want you to create a material that looks something like this. It has an if-define engine, which basically looks for whether we are in the engine or in the shader. Then it defines a vector for color to be white. And then we also define an operator that takes in another material to check whether we have the actual same material here, and then it returns true. In order to be able to do that, we need to add color white and the equals operator to vector 4. And in order to do that, we have to switch into the schnitzel lib. And then we switch over to the section where we have the vector 4. Over here we need an operator to compare against another vector 4. We basically just compare all of the components. And then at the very bottom I want you to add in a bunch of default colors. For example, we have color white, red, green, blue, yellow and black. Very simple colors. And then we can use these in the shader header. Now that the errors are gone, we can take a look at this. By default the material has a color of white, and that is just in the engine. In the shader it is just going to be a vector 4. This will allow us to create an array of materials inside of our shader, and we are going to do this in a second. First, I want you to go back to the rendering interface, and then at the very bottom where we draw our text, we can now take a look at what we have to do here. A transform needs to keep track of which color to draw the transform in, and in order to do that we need a getMaterialIndex function that takes the material in and gives us an index into an array of materials corresponding to the correct color. In order to do that we have to change the transform, and for now I would like to get rid of the float layer and swap this out for material index. Now that we have the material index on the transform, when we switch back to the rendering interface, we also have to get the material index function. And we do that in the utility part of the renderer. Right here in the utility section, go to the very bottom below the animate function and then add in the material index function, getMaterialIndex. Basically what it does is it loops over all of the materials in the renderer. If it finds a material that is the same material as our material supplied, then it returns this material index, because we don't need to add another one. If it doesn't, then it returns the material index on the new material that we are going to add to the array. And that means we need to add an array to our render data at the top here. So over here we generate a new array for materials, and also I would like to generate a new array for UI transforms. The reason why I'm generating this now is because it is easier later on when we switch to the renderer, and then I will explain that there to you, because we want to split the game from the UI. Okay, now that we have materials transforms and UI transforms, at the very bottom we should be almost okay. When we render a character, we could look at the glyph, we get the data for the material index, then we set the position of the transform based on the glyph's offset times times the font size. By default, the font size of every glyph is going to be 1. We do this for X and Y. Then we generate an atlas offset based on the texture coordinates of the glyph. Then we set the sprite size to the glyph size. And then we set the transform size using the glyph's size multiplied by the font size. And we have another one here for the Schnitzellib. We need to implement a multiplication operator in the vector2. So yeah, we go back to that, to where the vector2 is defined, and then we copy this operator for the division and we turn that into a multiplication. And now the rendering interface should no longer complain here. Basically, we are scaling the transform's size to the font size. And then at the very bottom, this is the interesting part. We take the rendering options. For now, it won't do much, but we're going to add in more rendering options in the future. Like, for example, left aligning text, right aligning text, center aligning text, stuff like this. I'm not going to cover in this tutorial. It is very interesting. If you want to find that out yourself, you can do that. But basically what we need is a rendering option that is rendering font. And this one has to be defined in our shader header. So we switch back to that and then we add another bit for the rendering option font. And this will conclude our render text function. Basically, we add the rendering option for font to the transform and then we add this transform to the UI transforms. This is why I added this earlier, because we are going to separate the game from the UI. And then at the very bottom, we advance the position using the advance of the glyph. In case you lost track of it already, this is the advance. It covers the entire character and maybe some padding to the left and to the right. It's the very bottom line here. Before we continue though, make sure that you go to the draw sprite function where we generate another transform, of course, for the sprites. And then please paste in the get material index function, assigning that to the transform material index. Because if we don't, then the material index is always going to be 0 for every sprite. And that could correspond to something else that we are not actually interested in. We have done a lot of work on the CPU in the engine. Now I want you to do some work on the GPU in the fragment shader, most likely. Up until now, in here, we just indexed into the texture atlas and then we drew the texture color to the fragment color. I want you to get rid of this and instead I want you to do the following. At the very top, we get ourselves a material using a material index and we get to that in a second. Then we check the rendering options that we will supply at the very top here as the input. Basically, we are checking for font. If we do so, we index into the font atlas instead of the texture atlas. Then we check whether our red component of our texture is 0. Basically, there is no color to be had here. And if not, then we assign the fragment color to the texture color multiplied by the material color. And at this point, it might be a good idea to add in these materials. So quickly to recap, bindings for the uniforms when it comes to textures, they correspond to the texture slots. So for example, binding 0 corresponds to texture 0 and binding 1 corresponds to texture 1. Now we have input buffers and unfortunately they have the same naming here. In Vulkan, this is better because there the bindings correspond to the actual bindings, and if I were to use the binding 1 here and the binding 1 for the texture as well, then Vulkan would complain. Unfortunately, OpenGL seems to keep track of these differently than of the buffers. This is a storage buffer object and these are uniform samplers, meaning OpenGL internally keeps track of these in different ways, even though they have the same naming here. So this binding is number 1 because in the Vertex shader, we use binding 0 for the transforms. And so we can't use binding 0, so we have to use a new one. Again, this is hard-coded because we are making a specific game. We're not making a generic engine here that is perfectly able to do any case scenario that you could ever think of. We're making a specific game and therefore we're making our lives as easy as possible by making the specific things or doing the specific things that we want for this particular game. Just wanted to point that out in case you guys are wondering why we're doing this, why we're hard coding this. It's just easier. So we get ourselves the array to the materials and then we can index into them if we supply them at the very top, the input. We get ourselves flat rendering options and flat material indexes. Basically what this flat keyword means is whenever we have two vertices, in between the two vertices, if we have one value here and another value here, in between those, the GPU is going to try to interpolate between them. But we don't want this for the rendering options, so we're just going to supply a flat keyword here to basically tell the GPU, please do not interpolate between the two, because they're most likely going to be the same, so there's no interpolation needed. We do that for the rendering options and for the material index. And then we use this material index to get ourselves the material, and we apply the color of the material using multiplication. And so yeah, this is our fragment shader. And obviously we also have to change the vertex shader now that we have more data. So in the output section here, I want you to add in two more fields for rendering options and the material index. And then also I'd like to do some cleanup here. The input is not really used, and this is actually the buffers here. This is the buffer section. And then further down below in the main function, we need to assign these or supply them to the Fragment shader, specifically talking about the rendering options and the material index of the transform. We save this, and this should be everything that we have to do in the shaders. I want to do a quick intervention here because it's already been going on for a while. I know this is a lot of code and a lot of things to cover. If you need to pause and then think about what everything does, I know these tutorials can get quite overwhelming, so take your time with them. Speaking of keeping track, now that we have changed the shaders and we added in an array for materials, we also have to add this into the renderer, of course, right? So we have to change to the GL renderer, and first I would like you to go to the very top and then add in another ID for the materials, transform storage buffer object ID. And then in the GL init function right below where we generate the buffer for the transforms right here, we add in another section to generate a material storage buffer. First and foremost, we generate an ID using glgen buffers, then we bind the buffer base using a storage buffer, and then we allocate a buffer of the size of the materials using the maximum elements, so 1000 materials will be able to be held on the GPU, and then we add in the dynamic draw option so we can use subdata, which means that now we can go into the GL render function and clean up a little bit. In my opinion, it looks better that way. So essentially I want you to create a local scope when we copy over the screen size to the GPU. Then I want you to create a local scope for the orthographic projection of the game camera. And then I want to create another local scope for the game pass. This is basically everything that has to do with rendering the game. Once you have this, I want you to add in another section to copy the materials to the GPU. Basically what we have to do here is we bind the storage buffer, and this is using the index 1. This corresponds to the binding again. So if we go into the Fragment shader, this corresponds to this number 1 here, the binding. Again, hard-coded, not going to go over it again. And then we use the subdata to copy over all of the materials that we have allocated this frame into the buffer. And after that, we clear the materials for the next frame. Now we need to make sure that we rebind the transform buffer. So below this section, bind back the transform buffer using slot 0 and the transform storage buffer object ID. If you don't do that, then the game will think, or the engine will think, OpenGL, that it needs to copy over into the material buffer, and then this one will hold garbage data. So make sure that you do this, and then in the game pass we can go quickly over this. We calculate the game orthographic projection, then we copy over the transforms to the GPU, we draw, and then we reset. And we do the exact same thing. We can copy this and paste this for the UI, but instead I'm just gonna show you what we use in the UI pass. We generate an orthographic projection using the UI camera, and then we copy over the data using the UI transforms. You can see here that we're using them all over the place. We draw the UI transform count, and then we reset the UI transforms. Okay, but we have still not done. We also have to initialize or change the game a little bit, just a little bit. We have to go into the initialize function of the game, and I noticed that the last time actually the camera for the game is here, some parts are here, and then some parts are at the very top right here. I would like to clean this up a little bit by doing the camera initialization for the game here, and then the camera initialization for the UI. You might have noticed that the UI is actually the exact same camera. Yeah, I'm supplying the same size for the UI as the game, which means that we're going to have the same pixel coordinate space, if you want to name it that way. And then the game initialized, I would like to put this to the very bottom. I think that makes more sense here. And then please make sure that you get rid of these two camera position things in the middle of nowhere, because then it's neatly packed. I like this more. This is almost everything we have to do in the game. Obviously we would like to draw as well, right? So if we scroll down to where we have our fixed update loop, we can draw text here. For example, subscribe, like, and comment at a position of 0 and 20. Remember that our game is top left aligned, so over here is the 0, 0 anchor point, and then down we can draw. So that would be at the very top left corner of the screen, and then we use a material of color blue. This is basically using the C++20, I don't even know what that is called. You can access the members of a struct by doing .struct member, that would be the material, and then we can do .color and then assign the color blue. Building the game will result in an error. We have unresolved external symbols because FreeType needs to be included and it needs to be linked. If you take a look at the third-party folder and then you go into lib, you will notice that there is a freetype.lib file. And just in this case, I'm going to ignore the freetype.lib because then you can download the same file from the repository. So I'm going to push this into the repository as well. Basically, we need to link with this library. So we switch over to the build.sh, and then where we have our libraries here at the top. We need to add an include path. Basically what this does, the capital L third party /lib is an include path that the compiler will look in for specific libraries. So if it can't find a library in the default folder, then it will try to look into third party /lib. And this is where it will find the FreeType lib that we are going to link now. Now we should be able to build, and then if we run the game, you should be able to see text if you did everything correctly. I know this is a lot and it can be very overwhelming, so if you made a mistake, ask in the comments, of course, right, if you have a problem. One last thing I want to talk about. In the game we have a fixed update loop, and this update loop runs at 60 frames per second. If we have more frames, then it doesn't matter because it will only run or update itself 60 times per second. If we run slower, it will still update itself 60 times per second. It will just run at like 20 FPS. The game will feel laggy, but the update loop will always be correct. So that means there is a mismatch between however many times we call the simulate function and however many times we actually draw, which means that if we put this draw text into our simulate function out of here, and then we go into the simulate, and let's put this at the very top, and then we build, and you know, we can go into the game.header file, then say, okay, I want this to be 30 frames per second, right? I want this to be half. We go back to the game, you can see it's stuttering. Now I have a solution for this, of course. Basically what is happening, it draws at once, one frame, and then it doesn't draw at the next frame because its rendering happens twice as often as simulating. And so only half the time we're actually sending data to the GPU to draw this. So if you want to, feel free to experiment a little bit. At this point, we are almost done with the entire engine. We have almost everything. The only thing is missing, that is UI. Feel free to experiment. Maybe you find a cool solution that I didn't think of yet. But yeah, for now I will put this back in here and then I will push this to Git. I hope you enjoyed the tutorial. If you did, please leave a like and subscribe. I really do mean it. It helps a lot out. And the next time we're going to add in UI, you know, buttons, maybe slide buttons, something like that, text, fixing the text problem. Until then, I hope you enjoyed it. See you next time. Peace!